Okay, I think we're going to go ahead and get started. So today we just have a lecture, and then at the end we'll go over some of the lab a little bit. You know, that second problem looks kind of like nonsense right now, but hopefully after today it'll make more sense. Any questions before we get going on notes or anything? So I did not get a chance to grade exams. I had a job interview in California, and I got trapped in the Los Angeles airport for 30 hours. I got home at 3 a.m. last night, so I'm a little bit out of it. If I say something dumb, just throw something at me. So I'll get those graded today and tomorrow. Get them back Wednesday. So lab 5 due today. I did spend a little bit of time looking at the evaluations. I need to take a more detailed look at those, but some of the big things you guys asked for were a lot more practice problems and clarity in lectures. So those are two things I'm going to immediately work on. Make some more problems. You guys like the videos or just problems on paper? Both problems on paper? Okay. I can do both of those. Questions about any of that? The Dropbox is up if you need it. Okay, let's take a look at the relationships lecture. So it's a little tricky, so try to follow along. If I don't explain something well enough, feel free to stop me. We can talk about why certain things are the way they are. So a major problem we have in animal breeding is traits like milk yield, where we want to improve a trait, but there's a problem, and that is some traits are only expressed in one sex, right? What do we call those traits? Remember from Dr. Silva's class? Did I hear it? Sex limited. Good. So those are sex limited traits. Traits that only show up in one sex, obviously. So if we want to improve milk yield, and we want to do this by selection of males, how do we get at that value? We're not going to go milk the male, hopefully. So we're looking at male selection for a sex limited trait. This is a huge deal, obviously, in the dairy industry. So how can we evaluate a male for milk production? Progeny, right? We need to take a look at his daughters, how they perform, to see if his daughters do better than the average of the population or if they do worse, right? That'll give us an idea of his breeding value, and we can evaluate him for a sex-limited trait. So that's where we're going with this. So what we'll do is, what's done in genetic evaluations and progeny testing is we take information from not only progeny, but all female relatives. So performance of his mother matters as well. He's still related to his mother as well as he's related to his daughters. And use that to evaluate his potential for a sex-limited trait, his genetic potential. So that's the setup. That's why we need genetic relationships. They go into clearly progeny testing as well as national cattle evaluations. They are hugely important. So should be open now. So B is kind of vague. Let me clarify that. Genes in common mean they got those genes from the same individual. So everybody of the same species has the same genes, right? But we may or may not have got them from the same individual. So essentially A and B are saying the same thing. That's not enough of a hint. Everyone get a chance to answer? Good, so we got that figured out. So relative implies common ancestor, which implies they share genes that came from one individual, right? At some level. So what information really can we leverage given that knowledge? Essentially, we're saying we can leverage information from every single individual we have records for that's related to the animal of interest. So if we're evaluating a single male, we can use records to evaluate him from his mother, his grandmother on back, as long as we have records. And we can use records from his daughters, his granddaughters, and so forth. So everyone related to him will give us an idea of his performance because they share the same genes. So genes in common, that's essentially saying we're estimating the breeding value of that individual. So accuracy is another topic that's going to come up when we talk about breeding values. Accuracy depends on, we're talking about accuracy of a single male's breeding value. The accuracy of his breeding value is going to depend on how related the individuals are that we have records on. So if you can think about it, if we only have records for a single male's granddaughters, so 2 generations removed, and then we have another male who has records on daughters, is it kind of logical that the one with records on daughters would be more accurate because they're more closely related to him? So we'll talk about that as well. So why do we even bother with males? Why not do this on a female basis? So we want to look at the genetic potential of a female. You just look at her record, right? And we have a pretty accurate picture of what's going on. So in breeding structures, the way we do it, males have typically the largest genetic effect on populations. What technology is behind that? AI, right? We can take a single dairy sire, and there are single dairy sires with over 10,000 daughters in the United States. It's pretty common. They sell semen out, and it gets used. If he's a great bull, they keep using it until we have tons and tons of records for one male. So this pedigree, everyone remembers what pedigree is. That's the kind of the family tree you think about, how we're looking at who's related to who. Pedigree structure becomes extremely important in this. We actually use pedigree structure to estimate genetic potential. So this is a typical real pedigree. This is from it's actually from a sheep dairy farm in New York. So if you look at these individuals, so the circles are females, the squares are males of a certain breed. We go down and zoom in on a single male. You look at this guy right here at the very bottom. He has 34 daughters.
You're saying that males have the largest effect in the population. Is that only because of AI, or is that generally true in most populations?
Generally true in most populations, even in natural populations, because males can have many more. Typically, where we have a single progeny being born, they can have many more progeny than a female. So a female throughout her life, say you have a cow, she'll have 5 or 6. A male, even if you just let them go in a field, a male will breed as many as he wants, right? So this single sire had 34 daughters. So do we do AI in the sheep industry? Any sheep people out there? Is it common? Not really, right? It's kind of difficult. So this was actually determined through genetic testing, and that sire made those females natural service. But still, he managed to have 34 daughters out of that, right? If we look at this guy, looking at just female relatives, in total, he had these three sons, and they went on did this. So in total, we have 70 female relatives, and that means we have, for a single trait, 70 records, right? If it's just a single measurement trait. If it's milk production and they do multiple repeated records, that's even more, right? Multiply that out. So what's going on? See if I can get rid of that. Nope. If you look at the females, like this female right here, she has 1, 2, right? Following the line, she has 2 progeny compared to the 34 of 1. So that's where that genetic influence on a population really comes into play. Questions on that? So we need to come up with a method to measure that relatedness. We need to put numbers on paper to get to that estimation. So here's our theory for today. In livestock breeding, selecting males is done using calculations based on degree of relatedness of individuals in the population. So relatedness to individuals that have records. So if we know sire A has a whole bunch of daughters, but only half of them have records, say half of them didn't get bred, didn't go into lactation, those half are essentially worthless for determining his value, right? For, say, milk production, because we have to have the record in order to make the estimation for his merit. So getting to the details of relationships, we said related animals have genes in common coming from a single individual. What does that do for us? First, we get resemblance in appearance. But the important part of today is resemblance and performance, right? Related individuals should have some degree of similarity in their performance. So we're going to use the term A sub XY to describe the additive genetic relationship. That's what we're going to call these relationships, additive genetic relationships, to quantify the degree to which two individuals are related. So a few lectures back in the central dogma of quantitative genetics slides, we said additive genetic relationship was one of the terms in our model. So you want to remember which one? It was that breeding value. So breeding value, hint, hint. You guys are getting some free points today if you're paying attention. Open. So remember back to those formulas. If we're interested in an individual's value as a parent, we're only interested in one thing, right? Because some of these terms are not transmitted to the offspring. Good, so that's a great test question right there too. Just if you remember value as a parent, what we're interested in, it's only the breeding value. If we were interested in estimating the individual's own performance, which one of these would we choose? Right, we need those three right there. So we need to dig into population structure and figure out how to look at a pedigree and estimate genetic relationships. So the most simple one we have is parent to offspring, X to Y. So we would say A sub XY. It's a half, right? That should be a logical assumption. Those two animals share half of their genes in common. Half came from there, half came from there. So our additive genetic relationship is just 1/2. So go one more generation. We've got this. We're going to look at the relationship between X and Y. So a grandparent and progeny. We have 1/2 between this individual and this individual. 1/2 between these two. So every generation we go further away, we take that and raise it to the exponent of the number of generations we have. It becomes 1/2 squared. So we get 1/4. It makes sense again, right? If you think about it logically, they share 1/2. We bring in another set of outside genes, so it drops to 1/2 again, and we get 1/4. Questions on that? Simple enough, right? So there's your formula. Additive genetic relationship between individuals X and Y is going to be just 1/2 to the T number of generations that they are separated by. So there's our T generation. So we have several situations that are very common in animal breeding that we can look at these relationships and kind of maybe memorize how they go because we see them so often. So we've got animals related with one common ancestor. In this case, we've got they share a sire. These would be half sibs. X and Y are half sibs. The formula does not change. It's still 1/2 raised to the T generations that separate the two individuals, right? So we've still got a line here counted as half, a line here counted as half. So these would be paternal half sibs. And they still share 1/4 of their genes in common. So we can also have full sibs, not as common in livestock maybe, but they're still there. So when two individuals, X and Y, have the same sire and dam, we go through the same process. We can go this way. We can go from individual X, one line up to its dam, another line down to Y. We also have another way to get there, right? At this point, we are tracing paths. We go from X up to the sire, down to Y. Both of those paths are 1/2 squared. When you have a case where you have more than one way or more than one relationship, you add them up. So 1/4 and 1/4, and we still end up with 1/2. Still following? Anyone want to ask a question? So the next thing we need to cover today is inbreeding and what happens to our genetic relationship when we have inbreeding. Inbreeding is also a common theme in animal agriculture. It's just the way things work. So here's your definition for inbred. An animal is inbred if and only if its parents are related. So that is the eye test for inbreeding, is you can look at a single individual's parents. If those parents are related, that means they share a common ancestor, then there's inbreeding happening in your population. So following that rule, if we look at individual X, the parents of X are this sire and this daughter. Those two are related. So individual X is inbred, right? is this daughter inbred? Who says yes? Is the daughter inbred? No, right? We don't know the relationship between these two, so we assume they are not related, so we say no, that one's not inbred, right? So just look at the parents and decide if the parents are related. Determine your inbreeding is present. So that relationship, here's the parents. Sire and daughter have a relationship of 1/2. It's not 0. So we call inbreeding there. So what about the relationship between this sire and individual X? Well, we can go from the sire to X directly. We have one path there. We have a second path where we can go from sire to daughter to X, right? We can go that way as well and find a relationship. Add those up, and that sire to X relationship is 3/4. So that means they share 3/4 of their genes in common. So thinking about that, what does that mean, really, in terms of that animal's genome? It really means 75% of this animal's genome is an exact copy of this animal, right? If it was 100%, what would we call that? A clone, right? We essentially clone something. So there are implications to doing that, as we all kind of know. We'll talk about those. So are there any questions on identifying inbreeding or estimating that? So we have actually a term for inbreeding. It's something we can measure and keep track of. It's actually quite important to measure and keep track of it in our population structures. So we call the inbreeding coefficient F sub X. So in more theoretical terms, the inbreeding coefficient is really asking what is the probability, so P for probability, what is the probability that both alleles at a locus are identical by descent? That's really inbreeding, right? So if you think about the 2 chromosomes, 2 strands of DNA, we get one from the mother, one from the father. If we have inbreeding, what happens is we get a buildup where we have allele A, which came from the father, allele A, which also came from the father, right? Those got passed down. Recombination, they ended up the same, and they both came from the same individual, right? So to get an inbreeding coefficient for a single individual, so say we're looking at the inbreeding coefficient for individual X in that previous little pedigree, it's 1/2 multiplied by the relationship of the parents. So if the parents aren't related, that being 0, that means we don't have inbreeding, right? If they have some sort of relationship, even if it's very, very small, we get an inbreeding coefficient which can build up. Open now. Good. So you guys got that. The only I guess item that quantifies inbreeding is the relationship of the parents. That's the only way we can tell if inbreeding is present. So if we want to go back and look at that inbreeding coefficient for individual X, F sub X is that 1/2 times relationship of the parents. We said this relationship is 1/2. We get 1/2 times 1/2. Our inbreeding coefficient becomes 1/4. Does anyone see something curious about the relationship between that sire and that daughter? In terms of what I've been doing following paths. Anyone want to ask a question about that? So you've seen me say, okay, we can go this way, we can go this way, we can go this way. If we're looking at the sire-daughter relationship, it seems like we could go this way, right? There is a path between those two, between the sire and daughter, and it goes through individual X. So we can't do that because the rule is when you're doing relationships, never go below the individuals you're looking at in the population. So given it's a vertical pedigree structure like this, you cannot add a genetic relationship by going down through progeny and then back up to an individual to get to a relationship. So that's one of the rules we're going to mention. Don't ever go down when you're estimating genetic relationships. Never go below the two you're interested in the relationship between. And why is that? Basically, this individual contributes nothing to that relationship, right? This individual is not contributing genes to that. Genes are not flowing that way, they're flowing that way. So think of it like a gene flow. They're not flowing up, they only flow down. So a point about inbreeding coefficients. Inbreeding coefficients will always be between 0 and 1. If you estimate an inbreeding coefficient and you get something greater than 1, check that out. It should be always between 0 and 1. So a way that we quantify inbreeding by looking at individuals is we come up with this meaningless statistic called an animal's relationship to itself. That may seem nonsensical, it kind of is, but we still use it for purposes of pedigree calculation. So we'll call an individual's relationship to itself A x sub x, so the subterms are the same animal. X and X, relationship to itself. It's simply 1 plus that inbreeding coefficient. So it's simply a way to keep track of, is this animal inbred? Is this animal inbred? It shows you who's inbred and who's not, right? There's no inbreeding, relationship to itself is just 1. If there is inbreeding in that animal, we tack on that inbreeding coefficient. So the last thing we're going to talk about is correlation between breeding values. I fixed that not 5 minutes ago, and it still goes to capital. So a breeding value, we said, is the value of individual alleles or the value of an individual as a parent, right? So it makes sense that the correlation between two animals, breeding values, say we're saying looking at the correlation between the breeding value of animal X and the breeding value of animal Y, in this case, R being the correlation between those two breeding values, has to do with the genetic relationships involved, right? So it's the genetic relationship between those two individuals divided by the square root of each one's genetic relationship to itself. So what does that give us? What does that number tell us? Given it's a correlation between breeding values, it's an approximation of the correlation between performance of the progeny. So add the word progeny right here. Performance of progeny. Because it's a breeding value, it's only relevant to the progeny. So why do we need all this information right now? We're about to get into estimating breeding values of individuals. That's the real number that kind of forms the foundation of animal breeding, is an individual's breeding value. We're going to get into estimating those using these types of relationships with multiple records and correlations between those breeding values. So here in a few lectures, it's going to become really important that we stay on top of using the word breeding value and being comfortable with what that means. Again, since it's a correlation, it's going to be between 0 and 1. Questions on that? So, short example, using this one, what's the coefficient of relationships or correlation between breeding values for sire Y and individual X? We said the relationship between them was 3/4 because there is some inbreeding going on there. This individual's relationship to itself, since it's inbred, ended up being 5/4. This individual's relationship to itself is just 1 because we don't know that it's inbred, right? Plugging all that in, we get 0.67. What does that mean? It's the degree of similarity in performance and performance of the progeny between sire Y and the inbred progeny X. So it's really a measure of genetic similarity, which gives us similarity in performance, right? How does that look when we don't have inbreeding? We simply have the typical sire-progeny relationship. Plug those values in. It's still just our value of additive genetic relationship, 0.5, right? They share 50% of their genes in common. Their similarity in performance should be 50%. So what is those two examples looking at where we have inbreeding, where we don't? The reason we use inbreeding and don't avoid it in animal agriculture is clearly because it gives us similarity in performance, right? Similarity in genetic merit and similarity in performance. Do we want similarity in performance in a production setting where we're driving for specific traits? Yes, we do, right? That's where economics comes into play. We want all of our animals to do the same thing. We can estimate profits, we can estimate future performance very well, right? Questions on that? Let's take a look at the lab so we can get rolling on that. So problem 2 is what we're going to look at, right? We've done the take the next record stuff, so look at those. So on that, I'll draw part of it. Use abbreviations. So what are we doing with the bottom table part? What we're asking for in those blanks is genetic relationship between all individuals in the pedigree, right? Form a little matrix out of that and do all of them. So, should have brought my handout. Step 1 in doing this, as we get started, is to go along the diagonal of your entire table and write 1, right? So we know there's inbreeding. We're going to go back and get to that in a second. So step 1 should be along the diagonal, write a 1. That would be an animal's genetic relationship to itself. So the first one is Bushmaster, right? So square 1 would be the relationship between Bushmaster and Bushmaster. That would be 1 for now, right? Do we know who Bushmaster's parents are? We assume he is not inbred. Relationship to himself is 1. So the next thing we need to do is go to the next square. We've got relationship between Bushmaster and Queen Bee. So I need to start figuring out what paths I can take that connect them through genetic relationship, right? So can I go Bushmaster, Crazy 8, and Queen Bee? No, right? We said the rule is don't go below the 2 individuals we're looking at. We cannot go down, we can't go this way. So these 2 are essentially not related, right? That's the way it looks on our pedigrees. They don't have any ancestors in common. We assume they're not related. Additive genetic relationship is 0, right?
Do we go down or across?
So you can essentially, once you fill in the diagonal of 1s, you can go either way and leave the other half blank because it's a copy, right? It's a mirror image. So you can cross out 1 half of the table, either the bottom half or the top half. You just need to fill in. Ideally, you want to fill in the top half so it's easier for us to grade because that's where we put the We can go right here. That gives us a half, right? Just one line, one relationship. Can we go down through HH and then back up to crazy H? No, can't do that. Can't go below the two we're interested in. That's the only way we can connect the two, so the relationship, genetic relationship is one half. Keep going. Let's do questions. Everybody good? Do Bushmaster and so we can go Bushmaster, Crazy Eight. Who parted? Anyone know where that's from, by the way? Who parted was I believe he ran the Triple Crown a few years ago. He just had a hilarious name. Don't say it too fast. He was a Kentucky Derby horse. So, lost the train of thought. We can go. We get one half. There's one way right there. Go down through Crazy Eight as well, right? We can go down. So we've got two lines. There's a half. There's a half. That's estimated by 1/2 squared. There's two connections there. 1/2 squared. That becomes a quarter. Add those up and we get 3/4, right? That's the only two we can go on that one. Okay, so that's how that goes. I think you guys can figure out the rest. So you're going to get to, sorry, the 3/4 on that one. It also helps if you write down the paths that way, so it's easier to go back and say, how did I do that? How did I get a number if it's not right? So keep track of what paths you went through. Just write down the initials or something. So you're going to get to the last individuals where you have inbreeding happening, right? So HH is inbred, right? So what you're going to do is go back and estimate HH's in relationship to itself. So we said that was 1/2 times the relationship of the parents. So you can figure out the relationship of the parents. Multiply that by 1/2. Add it to 1, and you'll have his relationship to himself. So it should be A. 1 1/4, right? 1 1/4. Relationship to itself. Right? That's just a marker to keep your track of relationships. So you're going to go back and figure out which one of those needs to be increased to above 1. So essentially you're saying which ones are inbred. And if it's inbred, you need to go back and revise that 1 to make it more than 1, right? Questions about any of that? All right, let's see in class. I just captured today, so I'm trying to continue